Okay, this lecture is about calculating a specific definite integral. An example similar to this was done in the lecture 2 videos ago, but I thought it might be a good idea to do another one. Here's a question. Evaluate integral from 1 to 4 of x squared plus 2x minus 5 using the limit of a Riemann sum. That means using limit of areas you calculate by subdividing your region to several panels and then adding them up. So limit of sum of areas of rectangles or rectangular looking shapes. Let's see what is involved here again. We are going to go back to what the definition was. I don't really need to do a exact job of graphing this. Just assume that I have some function. I'm just reminding myself what is it that is involved here. We are starting from at some point A and ending at some point B. A and B for me are just this 1 and 4. F is this function that is written here. What was our process? Our process was to go ahead and subdivide our interval to n subdivision. So I had x1, x2, and so on it goes all the way up to xn. When we adopted the rule for calculating the areas, any rule would do, we just kept using the right endpoint rule because counting is a little bit more natural to us that way. So I go ahead, look at this rectangle, then this one, and if there's another one here, look at that one, all the way to the very last one. I consider all these rectangles. Go ahead, calculate the area of each, add them all up, make a sum. At the end, you have to take a limit. The limit is going to happen when the number of subintervals goes to infinity. So let's go ahead and remind ourselves what was the story. First we had a delta x. Delta x is how thin or thick these rectangles are. These are delta x's. Delta x is b minus a over n. Then we had our x's. We have x 0, 1, 2, 3, and so on. X number I starts at very left endpoint A, and then it takes I steps of this step size, I times delta x. Who's I? I could be any of these numbers, 0, 1, 2, all the way to n. I could be any number starting from 0 all the way to n. What is the area? Area is going to be delta x times sum of. So delta x is the base. I have to multiply by these heights. If I use the right endpoint rule, first one is fx1, next one is fx2, last one is fxn. So f xi, I ranging all the way from 1 to the last point n. That is going to be approximation area. Now if I go ahead, take a limit of this thing as n goes to infinity, I'll be getting my exact area. In any of these problems similar to this, this is stated problem, you have to go through the same procedure and put all the pieces together and find what the limit is going to be. One major item that you are going to need in all of these type of problems is that sum of powers identities. Easiest one was when you're just adding power 1 of ordinary numbers from 1 through some number. N times n plus 1 over 2. We gave a simple reasoning for that. If the powers are 2, it takes a little bit longer algebra to show that the answer is n times n plus 1 times 2n plus 1 over 6. If the powers are 3, you get, by peculiar coincidence, square of that, n squared times n plus 1 squared over 4. There are similar formulas for any power, just the formulas on the right hand side get more and more complicated, and it ties in with some advanced algebra. Okay, just keep these identities in mind. We proved at least 2 of these in class. You might try to prove this third one yourselves. Item number 1, that's nearly trivial. 2 we did in class. 3, perhaps you can do that. Okay. Now how do we proceed? We take our function. Let me rewrite my function again. We were interested in the integral from 1 to 4 of x squared plus 2x minus 5 dx. So what's my a? A is a starting point. What's my b? It's ending point. What's my delta x? b minus a over n. So that is 3 over n. What is my point number I? Remember, we were dividing our x's from x0 to xn. Each of them had its own coordinate. So we have to start from the very left point. Left point is 1. We have to take I number of steps of this size. So that's going to be 3 over n times I. What is I? I could be any number from 0 all the way to n itself. What's our function? Our function is just the integrand that you have, x squared plus 2x minus 5. We are going to need to see what is f at xi. So I write f of xi, just plug this one for x, 1 plus 3 over ni squared plus 2 times 1 plus 3i over n, then minus 5. Okay, open this thing up. You have to be good with algebra and quick, because there is a ton of algebra to do. So we have to improve our algebra skills, so this thing will, so that it will finish within our lifetime. So 1 square, twice the product of first and second, 6i over n, square of the second, 9i squared over n squared. Just multiply through 2 plus 6i over n, then we have a trailing minus 5. So that boils down to 1 plus 2 minus 5, that's a minus 2. 6i and another 6i is 12i over n, and then here's a 9i squared over n squared. Okay, what would be our Riemann sum? We have to calculate all of these function values and add them all up, and that is how we are going to get our Riemann sum. How do we calculate that sum? How do we clean it up? Well, that is going to be done by using those identities we just mentioned at the beginning of the lecture. Here, these are going to be crucial in cleaning up the expression that we have. This is our Riemann sum. I have to multiply the width of the regions by the height and add them up. So I have to go do the following. Here's a Riemann sum. Is it going to be equal to delta x? Our delta x was 3 over n times the sum of the value of the function evaluated all these points. So minus 2 plus 12i over n plus 9i squared over n squared. I ranging, now for using the right endpoint rule, start from 1, go as far as n. For left, that means 0 to n minus 1. These are the things I need to add up. I have to multiply by my delta x. That's going to be my Riemann sum. Once I have all of this under control, I have understood what it is, but I still have one more thing to do, which is the limit of that when I take many subintervals. So how do we proceed? First of all, we apply the so-called linearity property of the summation. It simply means if you are adding up several components, you can go add all the fellows of the first type, all the fellows of the second type, all the fellows of the third type, and then add them up later on. So I can write it like this: sum of large number of minus 2's, I from 1 to n, plus sum of all these type of numbers, 12i over n, plus sum of these type of numbers, 9i squared over n squared. Okay, linearity goes one step further. For the purpose of this summation, I is the variable, is the dummy variable. These other entities are constant. 9 and n squared, or 12 and n, are all constant. Here I go one more level, 3 over n. I can, for example, factor this constant portion and put it outside. That 12 over n can sit outside, and I will have sum of the numbers I from 1 through n. This one also, 9 over n squared, 9 over n squared, sum of I squared. I ranges from 1 to n. Here, due to its simplicity, you might get confused as to what is this one, but just to push it further, I can also factor minus 2 and put it outside. This is really minus 2 times sum of a bunch of 1's, while I ranges from 1 to n. So what does this mean? This means you are adding lots of minus 2's. Minus 2, minus 2, minus 2, minus 2. How many times? For every one of these i's, you are throwing in one more minus 2. I ranging from 1 to n. You're doing this n times. you can write it a little bit neater. You can factor your minus 2's out, and then you'll have a bunch of 1's. That's what this summation means. If you have 1 plus 1 all of 1 n times, the meaning of this times minus 2 will be the same as that one. Now I multiply by 3 over n, I get 6 over n. Excuse me, this is 1. 3 over n times 12 over n is 36 over n squared, I ranging from 1 to n. 3 over n times that is 27 over n cubed. I have minus 6 over n, sum of all the 1's, what sum of n 1's? Well, that's obviously just n. 36 over n squared. What is the sum of I ranging from 1 to n? I'm trying to add 1, 2, all the way to n. That's what this one is. That is sum of I ranging from 1 to n. You remember what that was? That's what we opened with. Sum of natural numbers from 1 to n. We have a formula for it, so we quickly just use that here. That's going to be n times n plus 1 over 2. Maybe I don't need the other parentheses, I just drop it. How about this one? 27 over n cubed. Do you remember what was sum of I squared? Sum of I squared means what? 1 squared, 2 squared, so on all the way to n squared. So here, remember what was the formula? N times n plus 1 times 2n plus 1 over 6. So this is the Riemann sum for n subintervals if you choose to calculate each subinterval on the right endpoint of it. So this would be our Rn in our old notation. Right endpoint, we use the letter R for that. We had n subintervals. We just cleaned it up. For what function? This was our function. What was the region? Region was from 1 to 4. Okay. Now we are almost there. What is left to do? What is left to do is perhaps either to clean it up and then, more importantly, find out what is the limit of Rn as n goes to infinity. What is that going to be? Well, that is exactly the value of the area we are looking for. It's the definite integral that we are looking for. That is that original problem we started with, which was 1 to 3 of x squared. Excuse me, it was 1 to 4 of x squared plus 2x minus 5 dx. That is what is left to do. Now you can do it one of two ways. You can find the limit quickly. If you have done a lot of limit problems at the beginning of a semester, it will be very easy for you to find the limit without doing too much algebra. Or the alternative way of doing it is just to clean this up and then go ahead find the find the limit after algebra is all cleaned up. It all depends on your style and the way you prefer to do things. Here I just go ahead and show you a little bit of the tricks that are involved. Let me see if I can show you a few of the shortcuts here. Suppose you want to calculate this limit of Rn, and you're pressed for time and you have to do lots of other things. This is just one in a zillion other activities you have to do. Okay, the first one is easy. Here, of course, the n and n here cancel out, and all you're left with is just a -6. So here I have -6. How about second one? Here you see that denominator is n squared, and in the numerator you have n times n. When n is large, this n squared and this n squared are going to take care of each other, essentially cancel each other out. When n goes toward infinity, this 1 is not going to play any role anymore. This n squared and this n squared here are comparable and they cancel each other out. All that you are going to be left with is this 36 divided by 2, that is 18, and then what we are left with. Step 3. Here in the denominator you have n cubed. In the numerator, the largest exponent that you have is coming out of n times another n times another 2n. Of course, there are these ones here, but they are small change compared to what n is. And remember, n is going to infinity. So if you add 1 to it, it's not going to make a dent. If you add 1 to this, it doesn't make a dent either. So n cubed times n times 2n, the numerator is as large as really 2n cubed. That is leading term of the numerator. Now you can ignore all the other little items. When you're taking a limit, you can do the so-called leading term analysis. Just pick that. Now n cubes and n cubed cancel out. You are left with 2 over 6 times 27. Well, that is going to be just 9. Is that right? So that was a quick and dirty way of calculating the limit without going through all the stuff you have learned in either beginning of your calculus class or a pre-calculus class or something like that. So what do we get for the total? For the total, I believe we are going to get 21. That is the limit, and that is what we claim that definite integral, or the area under that between 1 and 4, signed area under that between 1 and 4 is going to turn out to be just 21. That's going to be final answer of this problem. Okay, now I realize we went through quite a few algebra steps, and it takes a bit of a practice to master all of this thing, but you need to do that just to see what's going on here, what is happening with these Riemann sums, how to evaluate the limit in this kind of simple problems. Simple meaning that you are dealing with just a polynomial in the expression here. God forbid if it was something else, the problem will get really definitely out of hand, and then you come to appreciate what the fundamental theorem of calculus is going to give you.